Okay, in this video we're going to talk about interference, and specifically to do with sound waves, then leading on to light waves for young modulus, because really it's at that point where we can then utilise those kinds of observations to allow us to look to work out wavelengths and whatnot. Okay, so we start out with just as we suggested before. We can get constructive and destructive interference, and it's very important to see what can happen when this happens in sound waves. And we'll demonstrate this in the lab as well, with some sound waves in the lab when you come to the lesson. But what we've got here is we've got 2-point sources. Now what's important about these 2-point sources is they are sound. We can treat them as sound generators, or we can treat them as almost like a ripple tank where you have drops of water in the ocean. So for example, when you put a drop of water in a lake, say you put there's your drop of water, you drop it on there, and then you get concentric rings as the ripples ripple outwards. Now obviously if you did 2 at the same time, then what happens is you get this effect that is known as interference, where the waves interfere with each other in specific ways. So at points like that, we've got the peaks of our waves are interfering constructively, and so as a result we get an increased amplitude. Here, it's interfering with, this is a gap for this one, and this is its max amplitude, so that's not going to produce anything. That's going to be, for all intents and purposes, a minima, whereas here we have maxima as a result of the 2 amplitudes, or the 2 waves, constructively interfering. And we can see that happening more extensively in this animation. So if I press start, you'll see if I press start, you'll start to see the waves, concentric circles coming out, and you'll start to see the pattern that I suggested being created. Now we'll just wait until that populates all of it, and then we'll pause it and we'll have a look at it in more detail. So there is the effect of waves superimposing upon each other, and we're effectively getting interference pattern as a result of it. Now, you can see this point here forms quite a nice line. Now that, where all those lines are intersecting, is effectively a position where we're getting constructive interference. We're getting constructive interference because the peaks of those waves are interacting at exactly the same points. In between that, however, you'll see that part of this wave here is in between the other wave. And so as a result, we're getting a minima at that point. We're not getting a very high intensity. And you can actually observe that quite nicely in a ripple tank effect. And I'll show you that in a more 3-dimensional animation. So if I press play on this one. So obviously that is, we're looking at the kind of ripple effect there on the screen. And what you can hopefully see is that these dark lines where doesn't seem to be very much happening. I will show you this on the ripple tank in lesson as well. But we can actually, with this animation, we can make it 3D as well. So if I click 3D, you can see that really nicely there. You can see these lines coming out here. Now those are the minima. That's where you're not getting anything produced, because we've got effectively destructive interference. We're getting a minima. So if I go back to the first animation here, so just to highlight what is what, you may want to draw a picture similar to mine on the board. You may want to draw extra rings to show how that interference occurs. So I might state that this is constructive here, and this is destructive. I'll just draw that out here, destructive. And then we've got a second constructive point there. So, very simplistic kind of observation of that there. And as we can see, that happens throughout the wave. And when it strikes this wall here, when it's light, we get something completely different seen. Okay, we get something completely different. Now, when it's light, when we deal with light, obviously you can't see light moving through the air, but you can see it when it's being reflected off something. So oftentimes we utilize a screen. So we're going to introduce now Young's double slit. So imagine for a second, I've got a light source that is coherent and it is being transmitted through those double slits. It's diffracting outwards, and as a result of the interference that we get throughout this area here, we get light and dark spots created along the length of the screen that we're observing light on. So we get a bright spot here. Then we'll get a dark spot. And then a bright spot again. And then a dark spot. And so on and so forth. And the point being is that those bright and dark spots are being created because of the superposition of the waves when they reach these positions together. Now, depending on how far the light wave has traveled, depends on what you get, whether you get a bright spark, a bright spot, or a dark spot. Now, as you'd imagine, bright spots are where we get constructive interference. Whereas dark spots are because of destructive interference. So let's look more intrinsically at why that can happen. And again, I'm going to show you another animation here that will help us to explain why we get light and dark spots, and we can put some numerical values to it as well. So here we have is a basic representation of what's going on here. We've got our two slits side by side from a coherent light source, so they're both being emitted at the same position. And as you'll notice, you've got the light wave travelling through the air and striking the screen at Y here. Same here, we've got a light wave travelling through the air and striking the screen, and since they both travelled the same distance, then effectively they're arriving in exactly the same phase as when they left. So they left in phase and they arrive in phase. In phase means quite simply that we have waves that are going to combine constructively to give a constructive interference, and we get a superposition which effectively makes a bright spot, and the opposite for a dark spot. So what happens if I move this then? As I've suggested, there are multiple bright spots on here. Well, in order to find another bright spot, we need to move these waves to a position where they have effectively will still arrive in phase. One will have travelled further than the other. So one of these waves will travel further than the other, but they'll still arrive in phase because the difference between those paths is equal to lambda. We'll talk more about those differences very shortly. So let's increase the positionings of these waves. Oh, I've gone. Just going to keep going. Just going to fix that a little bit more. Right, so what you're seeing here is exactly the same. Notice how the waves arrive in phase again. The waves arrive in phase. And because they arrive in phase, it means quite nicely that we are going to get constructive interference, and hence we're going to get another bright spot. Let's see if we can find another one. Right, so I don't know if you can see it, but obviously at the top there, we're now still arriving in phase. We've had to move the waves, and you can see here, the path difference is outlined here. In this case, the path difference is approximately 8. Notice that the wavelength, you might not be able to see that on your screen, but the wavelength has been set at 4, and the path difference is 8. And so as a result, what we get is we've got a constructive interference, we've got a bright spot at the end there. What about dark spots then? Dark spots are slightly different. So we'll go back to our starting point, we've got a bright spot. Where would we observe a dark spot? Well, a dark spot would be where a peak meets a trough. So I had the dots before, peaks of both waves. Now I've got the dots on a trough for the red wave and on the peak for the other. So where the dots meet in this case would be destructive interference. So let's see if we can find a position where the dots hit the screen at Y and they are combining destructively. Well, look at that, I've managed to get that pretty bob on. So you can see here that the dots, they're going to combine destructively at this point. So if we go back to our diagram, that was constructive. Let's have a look, they're combining now so that the waves are doing, one wave is doing this, the other wave is doing this. And so as a result, we get that. Now that's really important that you realise that destructive interference in this case will create a dead spot where the two signals are exactly identical. You will get a dark spot created, and I can show you that in the lab. So that's the first dark spot. Now interestingly enough, the path difference here is 2. Wavelength is 4. Well, what we can have here is that means that we can suggest where our next dark spot is. It's going to be halfway between what a full path difference of lambda will be. So, let's have a look. So, at 4, there's our constructive interference again. And there it is again, there's our destructive interference. So you can see that they're arriving out of phase with each other. And as a result of that, what we get is a situation where we get a dark spot created yet again. So let's go over the rules for this, and let's see if we can draw some of our own pictures to explain what's going on here. So, first of all, let's start out with bright spots. So you get a bright spot on the screen when, if we draw our double slit again, there's our screen, we get a bright spot when the waves arrive in phase. So they arrive in phase. You also get bright spots, or well, you still get bright spots in a situation where we have a path difference which is equal to n lambda, i.e. one of the waves has travelled an extra distance of lambda, or a factor of lambda. So they arrive, where they arrive, one wave has had a path difference of n lambda. So when they arrive completely in phase, or you could suggest that they have a path difference of n lambda, you are going to get a bright spot created on your screen. Okay? And that is all giving, because you get a bright spot because you get constructive interference. Okay? So let's talk about dark spots then. So again, dark spots are created, as before, where we have a situation where the waves meet and they are out of phase. We state this as being completely out of phase. We can also suggest that they are 180 degrees out of phase. And there's also another word for that, which is also basically termed the waves are in anti-phase. Obviously, that's one of the arguments, so it's not just that argument. We can talk about path difference. This time, it's a factor of half lambda. So basically, one wave, where we get a dark spot on the screen, it means that one wave has travelled an extra distance of a proportion of half lambda. Now, how do we state this? Well, that means it needs to be an integer though. So it needs to be, we can write this out, that has a path difference of n plus a half lambda. So n plus a half lambda will be the path difference for any bright spot on the screen. So the path difference of n plus a half lambda, and that is because all of that gives rise to destructive interference. Okay, so that's destructive interference.